Okay, so welcome to our Eastern Washington University lecture series, and then also the Columbia Basin Geological Society. I really appreciate you guys coming tonight. I know there's some other things happening, but we do meet usually the last Tuesday of every month, and we're going to stick to it. And I can tell you, you made the correct choice tonight. Thank you very much. Because we have our Tom Brocher, you've probably heard me talking already. I've been trying to get to speak for our group for a long time, has published some of the most amazing papers in seismology that I've read, and I just very much look up to Tom, and so I'm excited that he's here to talk tonight. I sort of said he was the director of all earthquake science, which is probably true, but he was actually the director of the Earthquake Science Center for the USGS for a long time. I'm working in Menlo Park, and then now he's emeritus and traveling the world and getting ready to start again after COVID is done, like we all are. So I thank you guys very much for showing up today. I also want to thank Scott Burns for speaking last month. That was a great talk, and it's available on YouTube. And then next month, we're going to have Spokane's own Andy Buddington, and he is going to speak about going below the belt, the supergroup belt of the Priest River complex. Was East Antarctica our next door neighbor during the assembly of supercontinent Columbia? So it'll kind of be off Steve Box's talk last year, which was also on sort of Nuna or Columbia. Be a great talk. This one's going to be on October 20th, and I'll check the presidential elections and make sure that's not another presidential election night. I'll look at that. But without further ado, I would really like to thank Tom Brocher for coming out and speaking tonight on the large earthquake in central Washington. Thank you very much, Tom. Oh, sorry, Tom. I'm a jerk. Real quick, everybody, the chat is off, but at the very end, if throughout the talk, you can type in questions in the Q&A, and at the very end, Nigel will read some of those questions out. And then if you really like to, we might be able to turn your camera on so you can actually ask some questions to Tom. But I know it's going to be an exciting talk, and I really thank you, Tom, for coming out.
Thanks, Chad, and thank you, everyone, for tuning in tonight. I also want to thank one of the joys of science, I think, is working with other people. And I've worked with several people that I show on the bottom that bring in expertise that I didn't have, and it was a real pleasure to work with them and ask them questions that I had when I was thinking about this problem. So my title is meant to be provocative, and it's are we still seeing aftershocks from our large 1872 earthquake in central Washington state? And it's provocative because we don't normally think of aftershock sequences lasting for 150 years. So could the a very unusual earthquake cluster that we're seeing in central Washington state in fact be related to the 1872 earthquake? So that's the topic of my talk. So I'll be talking both about this unusual cluster as well as the 1872 earthquake. And in my talk, I'll first talk about what we know about the 1872 earthquake, where it was, how big it was, and so on. And then I'll talk about this unusual cluster of earthquakes. But why we're interested in clusters like we're seeing is that observations of long-lived aftershocks sequences are pretty unusual, but they do indicate that there is a direct relationship between the duration of the aftershock sequence and the slip rate of the fault that they happen on. So faults that are moving quickly, like the San Andreas fault, tend to have aftershock sequences that only last a few years to maybe 10 years, maybe a little bit longer. Slower moving faults like the Wasatch Fault might have aftershock sequences of 600 years or so. And then very slowly moving faults, such as, say, the East Reelfoot Fault, with a slip rate of only about a tenth of a millimeter per year, might have an aftershock duration of thousands of years. So this is an important point for estimating seismic hazard, because we need to know what are the true tectonic earthquakes versus what are the aftershocks. So sorting this out is important. And I know there may be some skeptics out there about aftershock sequences lasting so long, but there's been at least one really well-documented aftershock sequence that occurred following an earthquake in 1891 in Japan, magnitude 7.5 earthquake. And this is a plot that shows a number of earthquakes per day as a function of day following that earthquake. And so it extends out 100 years. And you can see that there's a steady decrease of the number of aftershocks that has persisted for more than 100 years. And in fact, this is one of the aftershock sequences that the famous Japanese seismologist Omori used to develop his famous Omori law. So we'll be getting back onto these aftershocks in the second half of the talk. The other reason that we're interested in this 1872 earthquake is just that it was the largest known historical crustal earthquake in Washington state. And so the red dot shows the place that we think is the most likely general epicenter of the earthquake, and the big circle shows you the whole region that felt the earthquake. And you can see that it wasn't just all of Washington, but it was also felt in almost all of Oregon, much of southern British Columbia, as well as parts of Idaho and as far east as Montana. So it was a very large earthquake, no doubt. But at the time, in 1872, this was just after the American Civil War, and Washington was very sparsely settled, only about 18,000 residents. And it wasn't even a state at the time. It was the population was too small for it to be a state, and it was a territory at the time. But you can see it had a very, very large felt radius. If we look at the earthquakes that have happened in Washington over a 40-year period or so, from 1976 to 2016, one sees, there's a lot of earthquakes in the Puget Sound area. There's earthquakes along to the south along the Mount St. Helens shear zone and the Western Rainier shear zone. There's diffuse cloud of seismicity in the Yakima Fold Belt. But what really strikes your eye to the east of the Cascade Range is this cluster, very tightly defined cluster of earthquakes in the Entiat area of Washington. And lo and behold, we'll talk about how this Spencer Canyon scarp, which we feel was produced by the 1872, is essentially coincident with the location of this earthquake cluster. So that raises a lot of questions, and it motivated much of the work I did in trying to refine our understanding of the location of the 1872 earthquake, as well as understanding this earthquake cluster. This slide is a LiDAR bare earth view of this Spencer Canyon area. And the red line that I've shown on here is drawn just to the north of the actual scarp. So if you look on this map, you can see the scarp is just below this red line. And you can trace it for about 6 kilometers or so. And I want to point out that this LiDAR image also shows at least 6 landslides that happened very close, within 1 kilometer or 2 of the scarp. This landslide in the center of the figure actually produced a dam for the drainage and filled up with water. And dead trees were noted in the pond that was created by this landslide dam back in 1884, so about 12 years after the 1872 earthquake. We'll look. The next figure we'll look at is a a figure of a landslide that's just to the south of the scarp in this area. And on that slide, the oldest living trees date back to about 1885. And I should point out that this is all work done by Brian Sheridan and his co-authors. It was first published in an AGU abstract in 2015. And I just learned from Brian that he's got submitted a manuscript for publication that's currently in review. Brian and his team also dug 2 trenches across the fault in this general vicinity, and I'll talk about the results, the highlights of those results in the next couple slides. So the next slide will be looking at this scarp and this landslide here. And this is a photograph taken by one of Brian's team. And this is a landslide where the earliest tree rings are date to about 1885, so about 12 or 15 years after the earthquake. And I'd also like to point out how sharp the headscarp of this landslide is. It's very, very sharp. It doesn't look much degraded, so it looks like a fairly recent landslide, just on that basis as well. But to go back to the scarp itself, so as I mentioned, Brian and his group dug a couple of trenches across the scarp, and radiocarbon dating of the colluvium in those trenches yielded dates between, indicates an earthquake between 1840 and 1890. So that brackets the 1872 time period. There's only 2 events that post the deposition of the Mozama ash in the trench site, which the Mozama ash was deposited about 7,700 years ago. So we're not seeing a lot of events. So they seem to have occur on the order of thousands of years apart. The scarp reflects offset on a northwest dipping fault plane. The scarp is 1 to 2 meters high, which if you look at empirical relations between scarp height and magnitude, suggests a magnitude of 6.5 to 6.7. The 6 kilometer long scarp itself is shorter than one would expect for such a large earthquake, and is actually more consistent with a magnitude 5.8 event. So I think in that case, the scarp length is not telling us, is not providing a very accurate picture of the earthquake magnitude. Now, you might wonder who cares about this earthquake? Well, there are some people that operate dams along the Columbia River. And I should point out that the Spencer Creek scarp is shown as this red dot, and it's basically right along the Columbia River. So it's very proximal to at least 4 major hydroelectric dams that are along the Columbia River. And in fact, Brian Sherritt tells me that the dam that may potentially have the most concern with the fact that there was this 1872 earthquake in this location is the Wells Dam, which is operated by Douglas County Public Utilities Department. The big black circle here shows you the 95% confidence region for a magnitude 6.5 to 7 earthquake that was calculated by Balkan using the seismic intensities, and I'll be talking about that later on in the talk. So the scarp is definitely located within the region of highest confidence to be the epicentral region for the 1872 earthquake, based on the observations of the shaking that were reported at the time. This is just a photo of some of these hydroelectric dams. These are major infrastructure problems, and the cost on the order of hundreds of millions, if not $1 billion per per dam. So any mitigation work that needs to be done for these dams is clearly going to be an expensive proposition. So in the next part of the talk, I want to summarize all the evidence that we have for the location of the 1872 earthquake near Entiat. And of course, the first and probably the gold standard, in my view, in terms of the evidence is the existence of the Spencer Canyon scarp and the fact that it occurred within the time window of the 1872 earthquake. But I'll also look at the distribution of the seismic intensities. These are, you can call these felt reports, how the shaking was experienced around the Pacific Northwest. We'll look at the duration of the aftershock sequence. Where was it felt the longest is a good clue about where the earthquake happened. And we'll also look at where the ground failures and the water effects happened as a clue for where the earthquake happened. And we'll look at a couple other things, but these are the main four pieces of evidence that are very strongly consistent with an earthquake near Entiat. So the earthquake has been studied since at least 1956 by Milne, who looked at felt reports from southern British Columbia. Coombs et al. Looked at all the felt reports that they could find. Malone and Bohr in '79 evaluated a more limited set of felt reports. Bakken in 2002 looked at both the location and the magnitude of the earthquake using seismic intensities of Hopper et al., which was a group from the Golden office of the USGS. They wrote an open file report in 1992, which was never published, but was referred to by Bakken. So in my 2018 paper, we published those intensities so that they would be part of the public record. And then Brian and his group's discovery of the Spencer Canyon scarp in 2014 and 2015. So to give you kind of a map view of where people have located the earthquake, Milne looked at only the data from British Columbia. So of course he located the earthquake in British Columbia. Coombs et al. Looked at all the felt data, and they actually preferred a location near Entiat. So they basically concur with later researchers. Malone and Bohr in '79 came up with two possible locations, one in the Entiat area, which they actually disfavored, and one to the north and east, kind of near the Cascade Range, at a depth of 40 to 60 kilometers. And I'll be talking about the evidence mainly from the aftershocks that you would not prefer that kind of subcrustal depth for the earthquake based on the robust aftershock sequence. Bakken, as I mentioned, came up with a solution in this big black circle that agrees with Coombs et al. and with the solution by Malone and Bohr, which they did not favor. The red dot again is the location of the Spencer Canyon scarp. So this is a map of the seismic intensities data that was used by Bakken et al. They were developed by Hopper et al. In the USGS open file report, which was never published. So in my 2018 paper, these are the intensities that we showed, and we described in detail how they were derived. And I just want to point out that this earthquake was felt strongly in places like within intensity 6. So intensity 6, things are falling off shelves, tables, your even windows are breaking. There might even be minor damage to chimneys and that sort of thing. So that was experienced in Victoria, on Vancouver Island, in Seattle, and even down as far as Portland. So much of Washington State really felt this earthquake very strongly, intensities 5 and 6 at least. Now, there's also the earthquake was felt out to a radius of about 650 kilometers, and the smaller circle here with a radius of about 270 kilometers includes all the places where some kind of ground effect was reported, a landslide, cracking of the ground, soils, water effects of fountaining, increased or decreased stream flowing, and that sort of thing. I don't want to go into too much detail about these intensities. They're in the paper that we published in 2018. But the bottom line is that these represent not one person's idea or view of the reports, and but they in fact represent the views of basically 10 different groups or 10 different people, and then the mode of the 10 different assignments of intensities was assigned to each location. 4 of these assignments were done by consulting groups, and the Combs et al. 1976 was actually commissioned because there was such a large scatter in the intensity assignments by the other 3 consultants that the Combs group was commissioned to take a look at that and try to develop a more consistent intensity assignments. And one of the things that was done by Hopper was that no intensity, they didn't assign any intensity that was based solely on any ground failure or water effects, so landslides, water fountaining, and so on, because these can occur at a wide range of seismic intensity, so they weren't felt to be as accurate as observations of damage to structures and human reactions. But the bottom line is that the assignments made by Hopper et al. Are really not that different from those by Combs et al. That gives us some comfort that we're converging on reasonable set of seismic intensities. And again, these are the intensities that Bakken and his group used for his analysis. So this is a close-up view of those intensity data. And again, the black squares show you the locations where there were only ground failures or some sort of water effect. And these were not used to assign an intensity, but I show them where I just wanted to show where they were so you get some idea that they extended quite far away from the suggested epicenter. So the highest intensities recorded or assigned were those near Entiat, which is labeled Winesop here, and near Wenatchee. Those are intensity 8. The next level of intensity 7 have a wider radius, but the highest intensities give you an idea of where the epicenter were, and those were close to Entiat. I should point out, in these older historical earthquakes, and looking at seismic intensity data, we are limited by the reports that were made at the time, which are limited by where people lived at the time. And again, it's worthwhile mentioning again that there were only 18,000 people residing in Washington at the time of the earthquake. So we don't have a lot of observations just to the north of the earthquake or to the northeast of the earthquake. And those observations we do have were made at some range from the earthquake. Another important piece of information about the location of the earthquake is where were the aftershocks felt the longest following the main shock in 1872. And there must have been a very large aftershock within the hour of the main shock, because within the hour of the main shock, you can see the distribution of felt reports of the aftershock was very large. Much of southern British Columbia, all of Washington, much of Oregon, and out into Montana were felt aftershock within the hour of the main shock. But within the next day or so, that region of that reported feeling aftershocks became smaller and smaller very rapidly. So that after a day, they were only felt within the southernmost part of British Columbia and kind of the northern half of Washington. And that region became smaller and smaller. And in fact, a year after the 1872 earthquake, only the area near Entiat, Lake Chelan to Wenatchee, reported feeling aftershocks. So again, that's a data point that's consistent with epicenter in the Entiat area. This is where one would expect the epicenter to be, where we felt the aftershocks the longest. Another point that favors an Entiat origin is the distribution of ground failures and the fact that they seem to be concentrated in the Entiat area. So this is kind of a busy map, but it's a close-up view of the Columbia River area near Entiat, and the big red line is the Spencer Canyon Scarp location. The kind of orangey rectangle is kind of a crude outline of this anomalous Entiat seismicity cluster that is still producing earthquakes. And so that rectangle, if you measure the dimensions, it's roughly 20 kilometers by 30 kilometers. That is the area of a fault plane that you would need to rupture to produce a magnitude 6.8 earthquake. So by coincidence, perhaps, or perhaps not a coincidence, that the area of the Entiat seismicity cluster seems to outline the area that may have ruptured in the 1872 earthquake area. At least it has the same dimensions as would be needed to produce that magnitude earthquake. So again, the LiDAR data indicate the scarp is dipping to the northwest. So most of this rectangle would represent, if that's true, most of this rectangle would represent the hanging wall above the fault plane itself. And there's some observations, I know they're hard to read, but the Ribbon Canyon landslide, and I'll show some pictures of it in the next slide, happened just north of the scarp along the Columbia River. If I can get the cursor back, just in this location, there was an artesian fountain reported where water was fountaining 20 or 30 feet high following the earthquake, and some new springs were reported in the Wenatchee area. And in addition to you'll remember the 6 landslides that I pointed out that were really very close to the scarp itself. So there does seem to be quite a lot of ground failure right in the Entiat area. This Ribbon Canyon slide is really very impressive. It's hundreds of kilometers long, and it's right up against the Columbia River. And it apparently went into the river, and you can actually see little bits of the landslide sticking out of the Columbia River still in this photo. And the reports at the time indicate that the landslide dammed the Columbia River, at least for a few hours, and backed up the river. There are both tree ring dating and dating of volcanic ashes that suggest that, and as well as personal accounts that are consistent with this landslide occurring right after the earthquake. And if you go there, and I encourage you to do so, there's actually a road sign that talks about the landslide, and it talks about the fact in the middle of this description, it says a huge rock slide stopped the flow of the Columbia River for several hours. And it was witnessed apparently by some Native Americans who were living in the vicinity of the slide at the time. Now I want to point out, I want to discuss very briefly two other pieces of evidence which are consistent with an Entiat epicenter for the earthquake, but don't necessarily require an Entiat epicenter. The first of them is that in the course of rereading through the newspaper accounts of the earthquake, we noticed that at 23 different communities, the reporters talked about the directions of the shaking. And this was usually noted by the shaking of the lamps that were hanging throughout the house. And it was, directions were reported either as north-south or east-west, northeast-southwest, or northwest-southeast, and so at 45-degree angles. If we assume that those shaking directions should be either radial along the ray pass, along the long ray pass, or perpendicular to the ray pass, we can calculate what the misfit of these reported directions are for the suggested 1872 epicenter location. And it turns out that you get the minimum misfit for the proposed 1872 epicenter at Entiat. Now, the point to be made, though, is that there is a very big area of misfit that's about the same as that of the proposed epicenter, and that's shown in this orange rectangle. So you could put an epicenter within pretty much anywhere in this rectangle and get about the same misfit. So it's not a very, doesn't give you a very tight estimate of the epicenter location, but it is definitely consistent with this proposed 1872 epicenter near Entiat. We also looked at one report of the difference between the shaking produced by the S wave, which comes after the P wave, for the earthquake by an observer in Olympia, Washington. And his report suggested that the difference between these two times was about 18 to 20 seconds. So of course there weren't any recordings of the earthquake made at the time, but we looked at one of these earthquakes in the Entiat area recorded near Olympia. I think this was a magnitude 3.3 event. So we can see the first line here is the P wave. That's the first arrival, and then the second wave, the shear wave, is this other arrival here. And we can see, and this dark gray line is this 18 or 20 seconds from the start of the P wave. So the observation does not match the Entiat location on face value. But if we look at look at this record, you can see that the P wave is actually very small. And then around about 5 seconds, 4 or 5 seconds into the recording, we see a larger arrival. So it raises the interesting possibility that the observer also did not feel the first arrival P wave, but a wave that was farther back into the coda, what we call the coda of the arrivals. And so this difference might be a little bit closer to the 18 or 20 seconds before the arrival of the S-wave. Again, it's not very convincing evidence, but I did want to talk about it because this observation has been talked about in many reports, and we wanted to show that it may not be that compelling, provide that compelling an argument for the location of the earthquake. But it's certainly an interesting comparison to make. So again, we have this, to summarize the evidence for the location and the magnitude of the 1872 earthquake, we have the Spencer Canyon scarp. The height of the scarp suggested at a 6.5 to 6.7 magnitude. The seismic intensities are consistent with an Entiat location and suggest a magnitude 6.5 to 7 earthquake. The persistence, the aftershocks were felt only in the Entiat area after about a year after the earthquake, and there is seems to be a concentration of ground failure and water effects in the Entiat area. So now we want to investigate whether the ongoing seismicity cluster at Entiat could represent aftershocks of the 1872 earthquake. And, you know, one of the biggest reasons we might think that is that there's just a spatial coincidence between these two. And I want to point out that this cluster, this Entiat cluster, is very unusual. You don't see anything like it in the seismicity of Washington State or Oregon, for instance, and probably not in British Columbia as well. And the fact that the Spencer Canyon scarp falls right within the cluster is very intriguing. And a better view of that is given in this slide, which is a blow-up of the cluster. Here, this funny blue line is the location of the Spencer Canyon scarp. There's a magnetic lineation that's observed that's kind of parallel to the scarp, trends kind of to the northeast. And all these dots are the well-located earthquakes in the cluster. The beach balls show you the focal mechanisms of some of the larger earthquakes in the cluster, and they're predominantly reflect oblique thrusting within the cluster, more or less consistent with the orientation of the scarp. There is some strike-slip faulting. These are the beach balls like this are more consistent with strike-slip faulting, but most of these represent thrust faulting. Again, I've just drawn a kind of an arbitrary rectangle around these earthquakes in the cluster, and lo and behold, the area of this cluster matches the area of a magnitude 6.8 earthquake. So that spatial coincidence is very real and very intriguing. If we look at the depth distribution of the earthquakes within the cluster, we see this kind of broad peak between 3 and 8 kilometers. And you should ignore this big spike at about 1 kilometer. That's spurious. Those represent location errors. But the well-located earthquakes have a broad distribution of depth, but they're all very shallow, between about 2 and 8 kilometers or so, and very few earthquakes deeper than that. If we look at the distribution of the earthquakes in terms of the magnitude, and these are the earthquakes reported for the past 40 years. We can see that, first of all, that the instrument catalog is complete down to about a magnitude 1.5. We can see the straight line would suggest the catalog is complete above that. But below that, we have this roll-off, so we're not capturing all the earthquakes. So between about a 1.5 to 3.3, the catalog is complete. And we really have very few events larger than 3.3, and no events that are greater than magnitude 3.7 in the past 40 years. So this is kind of unusual behavior. But the B-value itself, 0.99, is basically 1, is a very common garden variety type B-value. There's nothing to indicate that there's something unique or special about these earthquakes. And I should point out that we're not near a volcanic center, so these are definitely non-volcanic earthquakes. They have nothing to do with volcanism. We look at the rate of the moment release from these earthquakes. We also get kind of a linear trend, the very low rate of moment release, and it reflects the fact that we don't have big earthquakes. We just have these, the biggest earthquakes are magnitude 3.7 or so. If we do a Brune type inversion of this moment rate, we get a very low slip rate of 0.004 millimeters per year. So that's very, very small. So this fault, the fault that's producing this seismicity would be moving at a very, very low rate. And again, to give you kind of a time history of these earthquakes in the past 40 years, this shows you the magnitude 1.5 and bigger earthquakes. And if we plot these as a function of time, and I think these are all magnitudes, we get about 60 earthquakes a year in this cluster. And my plot here ends at 2016, and I just checked the past 5 years. We've seen 63 events per year, perhaps. So this rate is just ongoing. It doesn't seem to change in nearly 45 years of monitoring. So that's a very interesting result as well. So one thing we can do with these aftershocks is to see if the numbers of aftershocks that we're getting now is consistent with the magnitude and the time of the 1872 earthquake. And so we'll be using 3 different populations of aftershocks. We'll use the aftershocks that were reported in the day following the earthquake, and then basically there were no reported aftershocks for the next 28 years. That doesn't mean that there weren't any observations of, there weren't any aftershocks. It's just, I think it's because there were basically nobody there to report the earthquakes. So we start having felt reports going back to about 1900, so a gap of about 28 years. Up through 1976, we have a fairly small population of felt earthquakes. And then, as you've seen, we have, since 1976, we've been monitoring this area. And so we have an instrument catalog. So we'll look at these 3 different populations of potential aftershocks and potential aftershocks separately. We're going to use Omori's law that I mentioned at the beginning of the talk as implemented by Riesenberg and Jones. So this is a very standard procedure, practice. We'll use aftershock rate parameters that are appropriate for Washington State, and they do vary by region. So we do want to use the correct parameters, and so we want to use parameters for Washington. And so these are the parameters, and the B value is the same B value that we met that we measured. And so we're assuming a b-value of 1, but that actually matches the value that we measured. So at least in terms of that, that parameter seems to be accurate. So the immediate aftershocks of the 1872 earthquake, there was one particular eyewitness report at Wenatchee, about 20 kilometers south of the Spencer Canyon Scarp. And the eyewitness was woken up, and he reported that the shocks, which we would call aftershocks, which lasted till 5 o'clock Sunday morning. The earthquake itself happened around 10 p.m. Saturday night, were 64 in number, of which 8 were very severe. So we know that he felt 64 aftershocks, or at least that's what he wrote, but we don't know what he meant by 8 being very severe. So there's some guessing that has to be done about that. Then we have this period of time where we did have felt earthquakes, but we don't have that many. And it looks like, you can see the highest reported intensities from these aftershocks are intensity 6, so fairly strong shaking. And then we have intensity 5s, about 4 or 5 of those. But then we have relatively few earthquakes that were felt that had a lower maximum intensity. And we're very, very, very much deficient in numbers of earthquakes at these lower magnitudes. If we plot these numbers of cumulative earthquakes as with time, instead of the nice straight line that we got for the instrumental, we see this kind of very jaggedy curve, and that's reflective of the fact that the catalog is not complete, and it's definitely not complete at the lower magnitude felt earthquakes. But we're going to assume that the higher intensities we have a complete recording catalog of those events, and that's an assumption that may or may not be true. But the relationships between magnitude and intensity suggests that these largest earthquakes correspond to magnitude 4 to 4.8 earthquakes, and these tend to be felt over a wide region, and so there's good reason to think that these may be complete. And again, we have the current earthquake catalog that now 44 years old, and we're going to look at this region between magnitude 2 and 3.3, where we know the catalog is complete. So we're going to focus on those earthquakes. Okay, so what you get from this modeling is that numbers of expected aftershocks as a function of the magnitude of the main shock, which is plotted on the x-axis here, as a function of time following the main shock. So in the first 7 hours or so following the main shock, which would be relevant for the observations of felt aftershocks in Wenatchee. To be felt in Wenatchee, felt is at least intensity 2, which would require in Wenatchee at least magnitude 3 earthquakes. So we have 64 of those, and lo and behold, we can match the observed number of 64 with an earthquake between about 6.8 and 7. So that's consistent with the magnitude range that was derived from the intensity data. If we look at the number of stronger aftershocks, and again, we don't really know how strong they were, but if we assume they were at least intensity 4, we again can match the observations. And the width of this the width of the black line is just an idea of gives you the 95% confidence in the calculated values of the bar. of the aftershocks for 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 these parameters. So again, if the earthquakes that were reported as producing very severe were at least magnitude 4, we can fit the estimated magnitude. If it's a greater magnitude, say a magnitude 5, then these are probably too large. You would need too large of an earthquake, magnitude 7.5 or greater. But some of these aftershocks that were felt as being severe, very severe, may have been smaller events. If we look at now let's look at the interval between 1900 and 1976. These are the felt events. Again, we're only looking at the higher intensities of 5 and 6, which correspond to magnitudes of at least magnitude 4 or 5. We can estimate the correct numbers of earthquakes for the magnitude range 6.5 for the very strongest felt earthquakes, and we're getting up close to the magnitude 6.5, actually abutting against 6.5 for the slightly smaller events, which were intensity 5. So perhaps that's consistent as well. Now, looking at the catalog data from 1976 on, here we know the numbers of for each magnitude, so we don't need to do any conversion from intensity to magnitude. And for magnitude 2, a magnitude greater than 2.5, magnitude 3, we would estimate magnitudes of the earthquake somewhere between 6.2 and 6.5. So not no overlap per se, but perhaps not far enough away from the range of 6.5 to 7 estimated from both the SCARP and the intensity data to rule out the possibility that these earthquakes could be aftershocks of an 1872 earthquake. So could the Entiat cluster represent aftershocks from the 1872 Washington earthquake based on this analysis? I don't think we could rule that possibility out with the existing aftershock data. It's possible, of course, that some of these events reflect ongoing tectonic deformation, but I think this aftershock analysis does not require that. So to go back to aftershocks, durations versus recurrence intervals, this is from an important paper by Jim Dietrich in JGR in 1994, where he developed the theory of aftershocks. And he showed that there's a linear relationship between in log space between aftershock duration and the recurrence time. So if we look at an earthquake that has aftershock duration of at least 145 years, almost 150 years, we would predict a recurrence interval of between 1,500 and maybe 5,000 years. And this seems consistent with the fact that we're only seeing 2 events in the trench on Spencer Canyon Fault in the past 7,700 years. So we're seeing events every several thousand of years, and that is consistent with this theory of rate and state friction. These numbers here, these different lines indicate the ratios between the duration of the recurrence interval, recurrence time, and the aftershock duration. So typically, the aftershock duration, the recurrence times are 10 to 40 times longer than the aftershock durations. And these X's here are some of the aftershock sequences that Dietrich showed match appear to match the theory. So why are observations of long-lived aftershock sequences so uncommon? Well, the theory gives us one explanation, and that is if the recurrence intervals are really 10 to 40 times longer than the aftershock durations, then most of the time, more than 90% of the time, faults are not producing earthquakes. They're just sitting there waiting, accumulating stress, and not having an aftershock sequence or not producing earthquakes. So they're relatively uncommon. They should be relatively uncommon. We really shouldn't expect to see very many long-lived aftershock sequences. And of course, another point is that these aftershock sequences can be so long that they really pose a problem for us humans, because the monitoring really has to be maintained for multiple human lifespans, and that's very hard to do. And the third factor is that the most obvious of these long-lived sequences occur in places where the slip rates are very low, so they're not at plate boundaries. They tend to be in regions between the plate boundaries, and so that's not where seismic networks are usually positioned, and so they tend not to be so well recorded. The other question I ask myself is, if these earthquakes in the cluster are not aftershocks of the 1872 earthquake, what the heck are they? They're very anomalous. And I've pointed out before that if you do the calculation, you would calculate a very low slip rate for the fall, less than 1/100th of a millimeter per year. GPS data also provides low slip rates. And there was a study using INSAR data that for 10 years that showed no resolvable surface deformation in the region over the cluster, which again is consistent with very low deformation rate. And we just don't see we don't see similar clusters for other Pacific Northwest faults that also must have very low slip rates. So why are we seeing a cluster on this fault and we've not seen clusters on other faults? I guess you could lean you'd have to lean on the argument that those other faults have produced their earthquakes so long ago that aftershock sequences have totally decayed. But it's hard to explain these earthquakes otherwise. So this is a figure I showed at the beginning of the talk, talking about this linear relationship between aftershock durations and slip rate. And the Entiat cluster would definitely be on the low end of the fault loading rate, which again suggests that if this relationship is accurate, we might expect to see aftershocks in this cluster for thousands of years, which is kind of a mind-boggling conclusion. To better understand this cluster, Ray Sakir of Washington DNR a few years back deployed 12 temporary seismic stations over the cluster and around it to improve the earthquake locations and especially the focal depths, and to get more focal mechanisms to see whether we can actually image a fault plane produced by the seismicity, because currently we cannot. So that's work that's still, the data are all collected, the array has been removed, and so the data hopefully will be analyzed soon. So this is a summary of my presentation. We think that the Entiat area is the most likely candidate for the 1872 earthquake based on the Spencer Canyon Fault, intensity data, the aftershock data, and the locations of some of the large ground failures, water effects. The earthquake magnitude is also 6.5 to 7 is also consistent with the scarp height and the seismic intensity data. The modeling of the aftershocks in the Entiat seismicity cluster is consistent with an earthquake of this magnitude. And the long recurrence, the long duration of the aftershock sequence does suggest a very long interval between main shocks on the fault, and that's also consistent with just 2 events recorded in the trenching of the fault scar. And again, this cluster is very uncommon, and that makes it an interesting and challenging place to study. And the final point I want to make is that I don't want you to go away thinking that just because we have a low seismic hazard, low slip rates in the area and in this Entiat area, doesn't mean that there's no seismic hazard. The 1872 earthquake demonstrates that indeed we do get earthquakes in this region. They're not hot, they don't come frequently, but they do occur. And again, a magnitude 6.8 earthquake in this area would be damaging not only to the infrastructure near the epicenter, but as I pointed out with the seismic intensity data, strong intensities were felt throughout Washington, southern British Columbia, and northern Oregon. And so there could be damage, widespread damage produced by an earthquake in this location today. So I'll like to wrap up my talk with that point and try to answer any questions that you might have.
All right. Well, thank you very much, Tom. I have a couple of questions in the chat that may be pertinent. One from our dean, David Bowman. Have you thought about using the site conditions at the felt reported sites to adjust the MMI values similar to what Sue Howe has done for New Madrid?
I have not done that. No. It's a good point, and it may be worth a look, but I have not done that yet.
Okay. All right.
And I'd also like to point out, if you'd like to ask a question, you can press the raise your hand button at the bottom, and we can unmute you for a question as well. Thank you very much, Tom. That was great.
Yeah, first off, yeah, let's give.
Thank
That's
you.
Awesome. Chris Dahl asks that could there be kind of deep meteoric water circulation to lubricate the fault at depth and cause this periodicity? Kind of a...
Yeah, there definitely could be water getting to the fault zone. It likely was a shallow fault to produce a fault scarp. It definitely ruptured up to the surface. So it's definitely probable that water can get down that deep. I don't know if there's be interesting to know what mechanism could be suggested for why it should be periodic on the scale of thousands of years. But I'd be interested in hearing about that.
Another question from one of our former students. Do the dams monitor the faults? Is there some kind of, do they have active monitoring stations at the dams?
That's a good question, and I suspect that they do. I know in California, dams and big structures like this are generally instrumented. I can't say that for sure about these dams. Perhaps somebody can help me out, but I would not be surprised if they were instrumented. Because that's one of the first questions after you ask after following an earthquake is what level of shaking was experienced by the dam or the infrastructure.
Fantastic. Kenny asks that based on the information you provide, do you think that the overall seismic hazard may be higher than the long-term hazard model suggests?
No, I'm not suggesting that because as I pointed out, the slip rates that you infer are low, and so they are probably pretty well accounted for in the current model. It's not like these are high. It's not like we've taken a fault and assigned a higher slip rate to it. So I doubt very much if these would change the seismic hazard map, apart from if this were a totally unknown fault and we add it to the map, it might change slightly. But again, the slip rate is not very high. So generally you need a slip rate of at least 1/10 of a millimeter per year to show much of an impact on the seismic hazard map. And if it's 10 times lower than that, it's not going to show up in a major way.
And for those of us in Spokane, I'd like to point out too what Tom said right there. Low seismic hazard does not mean no seismic hazard, as well as we have our own Spokane fault.
Right.
Please keep that in mind. Yeah.
Right. Yeah. And in California, and I think in generally, it's these we're always looking at the Hayward Fault, the San Andreas Fault, the faults that are moving and that produce earthquakes on a frequent basis. But the earthquakes that are the surprising earthquakes are exactly this kind of earthquake that happen on faults that are moving very slowly.
Yeah. We got a couple more questions here. So this is from Ray, who's you also mentioned in the talk. Would it be a relation between population/human activity increased and the aftershocks increase?
That's a great question. Definitely for the felt earthquakes from 1900 to 1976, you have to have people there living there to feel earthquakes. If there's nobody living there, you can have all the earthquakes you want, and then there's nobody to feel them and to report them. So over time, it's probable that more humans living in the area, so perhaps more earthquakes were reported. But that's why I wanted to focus on only the biggest of the felt earthquakes, which would have a very wide felt area. And so they're not dependent on people living right in the Entiat area. They can be felt, people living in Wenatchee, perhaps even as far away as Walla Walla and other places where there is a larger population. For the, definitely for the earthquake catalog, that's what's really interesting, is that's not dependent on humans. That's an instrumental catalog. And that number is just flat for the past 45 years, 64 earthquakes a year. So that's fascinating to me. Yeah.
Great.
I see that Bill Rumber's got his hand up. So I'm going to press allow to talk, Bill, and then you can just click unmute. And then.
Okay. Is that better? Can you hear me now?
You're good.
Good, yeah.
I don't see my picture there like I did the last time I tried. This is my third time on Zoom, so there's some rough edges here. I have a question about the earthquake swarm in central Idaho. I grew up in the town of Stanley in Sawtooth Valley, and when more than 50 years ago, the USGS had a trailer out in Valley Creek recording reoccurrent aftershocks, I guess. But there was a huge earthquake down there this summer or last spring. And I'm just wondering if that is something that correlates with this, because as I listened to your talk, I couldn't help thinking about the correlation of those earthquakes that I saw, or that I remember as a youth, and then again last summer, the big swarm that hit there, because of I think there was it was an over 6.8 or something like that earthquake this summer. Do you know anything about that, Tom?
Actually, I'm curious about your comment. I don't know. I don't really know anything about this swarm in Idaho, and I'd love to learn more about that. But so I can't really address your question very well. But you say that this swarm has been going on for tens of years?
It was if you look at the earthquake map produced by Roy Breckenridge at the Idaho Geologic Survey, you'll see the largest number of earthquakes recorded in Idaho are right in that area where the USGS had their trailer set up. And this was more than 50 years ago. It was the late 50s, early 60s. It was there for about, 5 or 10 years. I can't tell you for sure. But then again, this summer, there's been many, many aftershocks after that large earthquake in the same area within 10 miles of that trailer.
Right. Well, that's expected for a crustal earthquake, is that you have many, many aftershocks. But typically, within 10 years or so, you don't really see many aftershocks. So it'll be interesting to see what plays out in that aftershock sequence. But that's what makes this Entiat sequence so unusual, is that typically we just don't see that. We don't see.
Well, it correlates very well with the earthquakes that I remember. Again, you remember in your youth when something is set up by the USGS to monitor earthquakes, and then again in more than 50 years later, you find the big earthquake hitting within 6-7 miles of the same spot.
Was that initial setup to record aftershocks from a bigger earthquake, like the Hepburn Lake earthquake?
I don't think so. I just think people had reported earthquakes there most of the time.
Okay.
It's associated with the genesis of why they set it up there. But you could find out, I'm sure. I mean, there must be good records of that trailer sitting there. I know it was set up to monitor earthquakes.
Yeah, that's awesome, Bill. Yeah, the Bora Peak earthquake was right near there in Asheville.
Well, the Bora Peak earthquake was quite a ways away from where this was. The big earthquake that hit there this summer was within 6 miles of where that trailer was.
Oh, okay.
And the aftershocks of that earthquake have been progressively moving south along roughly north-south. I've been monitoring. The USGS has a lot of records of that latest earthquake on their website.
Yeah.
You just go to Earthquake Idaho and it'll show you the one. And for a long time, you'd hear about it on the news from Lewiston. You'd hear about the earthquake aftershocks, and they went for, there must have been 50 or 60 of them that I remember. So I'm sure that they're still happening.
Yeah, I'll try to take a look into that.
Yeah, thank you very much, Bill. Yeah, if you Google, there's some really good
Where are you
videos
located, Tom?
on the Stanley earthquake. Yeah. We had one more person with their hand up, Martin. They have taken off there. I might use this time real quick just to say thank you everybody for showing up. I know it was a hard night to show up, but it was definitely well worth it. Tom, that was a great talk. I feel horrible I couldn't have my camera on to laugh at some of your great jokes in there. Who would care about this earthquake? And there's a great picture of the dam right there. I do want to just point out again real quick that I think Tom might be okay with us posting this on YouTube. So we have a YouTube link for EWU Geology Rocks on YouTube. Scott Burns and a couple other talks on there. Please come check it out if you can. There might be a couple more questions too. I do want to just point out, please support your local geology department. Our students all want to do research and money is very tight right now. So any help is greatly appreciated. And then I will, just thank you again for showing up. I'll let back to Nigel here from EWU to answer some more questions.
Yeah, I got. So this harps back to the concept that are there other places that we're seeing actively the similar pattern that Entiat's long-lived aftershocks have, Tom?
Yeah, well, there's a big debate about the origin of the earthquakes in the New Madrid area in the middle of the country. This is where in 1812 there were, I forget how many, 4 large earthquakes. And there's a lot of seismicity going on there. And it's been quite a debate about whether these earthquakes are tectonic and reflect ongoing deformation along faults, or whether they're long-lived aftershocks after the 1812 earthquakes. Let's see, if I go back, this figure shows some other places. Charlevoix in eastern Canada has a sort of clusters of earthquakes that are been proposed that an earthquake in 1663 are causing those earthquakes. And I mentioned the New Madrid area, but this is, we really would like to try to resolve this question if we could. How long can these aftershocks persist? Because it does matter in terms of figuring out the seismic hazard of places in terms of the existing seismic catalogs.
And one final question. Ray asks if these are the aftershocks of the 1872, then this is not leading to the big one, or they may be reactivated faults nearby? Question mark.
Yeah, that could be one interpretation, is that none of these earthquakes are happening on the main thrust that ruptured in 1872. They're just happening in the volume around that earthquake. But again, we don't see that very often. Whether they're on the main fault or on faults surrounding, all the geodetic information suggests that this is a very low this region is deforming at a very low rate. So why do we see earthquakes here and we don't see earthquakes in other faults in Washington, Oregon that are under stress at comparable rates? That's the question. Go ahead.
Oh, I was going to say, Martin, his hand's back up. Is it okay if we have one more question?
Yeah.
We'll allow Martin to talk. So, sorry, Martin, I think I double tapped there. Martin, would you mind clicking that mute? I didn't mean to.
Am I there?
Yes.
No?
No, you're good.
Okay, yeah. My only, coming back to the prior fellow talking about Idaho, when that happened, I think it was well over a 6 point something earthquake this year. And I looked it up on a topo map, and the topo map says Shake Creek, so I think it's been going on for a long time. Yeah, maybe not 64 a year, but certainly a long time. So I'm ready for a milkshake, that kind of shake I want. Okay, I'm done. Thank you.
Thank you, Martin.
Thank you.
Yeah, thank you. Thank you very much, Tom, and thank you guys for sticking around today.
Thank you, Tom.
Wonderful talk. Another addition to the EWU Geology and Columbia Basin Geologic Society. Have a great day. Thank you, Tom.
Chad, what's our next talk?
Oh, again, the next talk is Andy Buddington is going to talk about below the belt and his research over by Coeur d'Alene, looking at some older quartz sites below the belt supergroup. Should be a great talk. Those who know Andy know it's going to be a great talk. So thank you very much.
Cool. Thanks, Tom. Have a great
you.
night.
Thank you, everyone.
Cheers.